Today in chapter 13, probably finish it up, and then we'll go right into applications of UV-Vis, which is chapter 14, the next chapter. So I'll try to get those notes posted this afternoon. The thing that we were talking about are things that cause deviation from linearity and Beer's law, and we said there were a couple of major different types, and we went through just to review the major ones we talked about. So the deviations are real versus instrumental, and we talked about the real ones a little bit. The instrumental, there's two major types that cause the problems. Those are the polychromatic light and that of stray radiation. And polychromatic we fix by adjusting our monochromator to our proper setting. Stray radiation, which is the one we ended on, it's the one that's dependent on the quality of the instrument. So I gave you this formula for stray radiation. So you get this calculates an absorbance that's going to be measured in the presence of stray radiation. And then we look at the deviation from linearity. 1%, not bad. 5%, it loses linearity really quick. So this is where you get what you pay for in an instrument. A high dollar instrument is going to give you something that's less than 0.1% stray radiation. Today there's a new technology used to make gratings, and gratings used in the monochromators are now created using holographic gratings, and lasers etch the surface. So with that, they can control the processing, making those monochromators so that the gratings are very smooth. The smooth surface minimizes the stray light. And with this, Shimadzu has an example called the Low-Ray series, and their stray radiation is 5/10,000%. I mean, it's a really, really high quality stuff. And the thing that we usually think about doing calibration down here in the absorbance of 0 to 1, and maybe 1.5, and then we start to lose the linearity. But their instrument allows linearity going all the way out to 8.5 in absorbance units. So where that would matter to you if you're going to do something with a calibration that needs to cover a wide range, instead of being limited to just calibrating in this window, if I can now calibrate in this entire concentration range, that's in your advantage to make that purchase. So they're a little bit certainly more expensive. Shimadzu is one of the companies that produces that instrument. Another company, Eclipse, Carry, their Eclipse series also uses a similar technology in their gratings to allow you to calibrate. I think they claim 7.5, but absorbance units linearity. It's still a vast improvement in technology from what we could do just a few years ago. All right, the last type of deviation is the chemical. And chemical is an example of a real deviation. And this is where spectra shift due to a change in a chemical equilibrium. So we studied this to some extent while we looked at how pH causes spectra to shift. So if you don't have something that's buffered and the pH changes in the one solution versus another, it can cause the spectra to shift. We saw that with our indicators. Even just the effect of concentration can play a role. So in this example, concentration, this is a plot of the absorbance for a dye at a series of concentrations going from 0 times 16 times 10 to the minus fifth. So it's in the micromolar range, really low concentrations. But this is a highly ionic dye, and the presence of just being around the other dyes cause this molecule to shift in its spectra. At the two different wavelengths, one goes down, one goes up. So it's an indicator. You've got like it wouldn't be a change in pH, but the spectras are not linear with it. Something we talked about last semester is the influence of ionic strength. The ionic atmosphere influences the extent of an equilibrium. Okay, so if you made an analysis in a sample that had an ionic strength of a very low salt concentration versus that in a much higher salt concentration, you're going to see a shift in spectra. Okay, so that's going to, comparing those two things, the delta or difference. There's going to be a shift in the spectra. Sometimes it's going to shift in the blue light direction. Sometimes it's going to shift in the red light direction in terms of the wavelength max. Sometimes it's going to suppress the signal. Sometimes it's going to enhance the signal. It really depends on the electronic structure. So that one, the change in ionic strength is something that you have to be careful with. And if you have samples that are sensitive to that, you use what's called an ionic strength fixer. And what this simply is a solution of very high ionic strength that is added like in a 1-to-10 ratio to all the samples in the buffers, and it would overpower any ionic strength that's coming from the sample and let it be at a fixed ionic strength, comparing samples to standards. So ionic strength fixers are used if that becomes the case. And all you need to do is create a salt with it. It's going to have a very high ionic strength in the system. All right, let's talk about the quantitative side of it a little bit. So we know it's based on Beer's law. So absorbance is equal to epsilon BC. Just keep in mind that's defined at a given wavelength, whatever we choose that wavelength to be. So we can use this to determine the concentration of an analyte. And the process that we do is we choose the wavelength. What is this lambda prime going to be? All right. We do something to hold the path length constant as we can. So a QVAT accomplishes that, preferably a square. The molar absorptivity determines the slope of the calibration curve and the linear dynamic range. So when I say that, when we think about a spectra, a plot of lambda versus absorbance, and we've got a peak that's in here, keep in mind that if we plotted the molar absorptivity, the molar absorptivity would be a mirror image of this. It's just at a different scale. So the absorbance is a function of molar absorptivity, directly related. So these things are directly proportional. So those two terms are not changing. These are fixed when we do a spectra. All right. So the thing that's changing is the molar absorptivity changes with the absorbance. So if we want something with a lower slope, we could go down to this peak versus a higher slope. So if we compare the slopes of the calibration curves, what would happen would be slope 1 would be greater than slope 2 because the higher absorbance there. Ideally, we want to choose a wavelength where we don't have spectral interference between other components in the sample or the solvent. Sometimes if you don't know what your matrix is, that's a tough thing to do, but you do the best you can. And kind of the steps we do is we dissolve the sample in a suitable solvent. Sometimes that requires some type of a pre-treatment, maybe like a digestion of a sample. Sometimes it's filtering. There's a lot of sample treatment that you have to do. In fact, that's a course in its own. Choose your wavelength, and then, like we had to do yesterday, dilute until it falls into your calibration window. Okay, so if it's above your linear dynamic range, you have to get the sample in that window. All right, so our clicker question for first one. All right, so what a point for being here today. All right, one is blank. All right, so switching to the instruments. This is where we can have a lot of variation in the technology of the instruments. We can have something that's extremely simple. In fact, we can have completely handheld, field portable spectrophotometers that can measure a sample in the field, to something that is very, very complex, even more so than the Spec 20 for research grade instruments. You get what you pay for, basically. Performance is going to be defined as the precision the instrument can accomplish, the accuracy, and it all comes down to the big dollar sign. What can you afford? Your lowest end types of instruments are going to cost in the neighborhood of $1,000. Today, the kind of the amazing thing is $1,000 will actually get you something with some scanning capabilities. If you go with something low-end, like a photodiode array. So I've used this diode array for demonstrations for y'all, but I've put together for my other class. This is actually holds a cuvette, and it has an LED light source in it. So if I want to, now I can drop a sample in, and I can use it to collect the entire spectrum on a sample to get absorbance measurements. It's not the highest precision, and it's got limited to the visible wavelength only, but it's every bit as capable as the Spectronic 20. Okay, so the downside to it is you have to have a computer connect to it to run the software to control it. So it gets every extreme to have in between. So things that you have to consider: what is the initial cost of the instrument? What type of maintenance costs are required? So is it something that's going to require, if it's an instrument that's on 24 hours a day, even though you may pay $12,000–$14,000 for something to acquire UV spectra, and if this instrument's on 24 hours a day, we have to realize that a UV lamp is going to cost anywhere from $1,000 to $2,000 to replace, and it's got a 1,000-hour shelf life or $1,000 operating life, and then 1,000 hours you got to replace that. So I mean that's a couple times a year if you've got an instrument that's running all the time, like in a quality control lab, where it's never going to be turned off. What's operator training is required? So for the user to use the instrument correctly and get the results we want them to get. And then the other thing that's probably the biggest factor that relates to cost is what is the actual resolution that I need. And I copied this figure out of the text. So this is an example of a benzene vapor. We talked about it before at some different settings on the instrument. So this is an instrument with adjustable bandwidth. So is 2 nanometer bandwidth required? And you can see some of the hyperfine splitting in it. Or is 5 nanometer required? Then you can just kind of make out where the maximas are. If it's 10 nanometers, all the instrument's capable of, it's going to be barely even see shoulders there. If it's 20 nanometers, it would just be around feet. Okay, so what's required of the instrument? Do you really need to be able to distinguish these things that are 1/10 of a nanometer apart? If you wanted to do the analysis, the first lab we did to look at cresol, resorcinol, phenol, those maximas only varied by about 8 nanometers. You couldn't tell them apart on a Spectronic 20. You just don't have the resolution there. So what do you need to do? So the wavelength range becomes a factor. Do you need something to do UV? If it's going to have to do UV to go from 200 to 350, 380, then you have to have a deuterium lamp and the power supply that backs that up. That at minimum is going to add $2,000 to the cost of the instrument. All right. If it's just visible, that's going to be your cheapest option because you can run that off of a tungsten filament lamp that's very cheap and very simple to operate in terms of electronics. Or do you need to be able to scan the entire UV vis spectra? Then you're going to have both in the system. What accuracy is required? So how well does it do? And we think about accuracy in a couple of different ways. Number one, what's the wavelength accuracy? So if I tell it to go to a particular wavelength, lambda equals 260.343 nanometers, is it really going to that wavelength? And secondly, in terms of making the measurement, if it tells me the absorbance is equal to 0.347, is it really 0.347? So both of those things we think about. If the spectra is off, instead of measuring the point here, if it's actually making the measurement slightly over, obviously that would give a different signal. And the difference in the signal could be significant at some time. So we have to make sure we get what we want. And then really gets expensive are the frills, the add-ons. So auxiliary equipment is the terminology we use to describe that. Does it need temperature control? So if you're doing something that's temperature dependent, do we need that? Do we need multiple cells? So the Shimadzu instrument, at some point when they purchased that instrument, the decision was made that they wanted to be able to do kinetic studies, so they wanted to do temperature control, and they wanted multiple cells so they could switch back and forth between samples. To my knowledge, that technology has never been used, and it was probably a $12,000-$15,000 add-on at the time when they made the purchase. A grant paid for it, but it's just hasn't been utilized to the extent that maybe it could have. Flow injection. So flow injection is a way that you can continuously monitor a sample. So it's got basically a flow through cuvette. So if you wanted to monitor something in real time as it's changing, you can get a flow injection cell. Okay, looking at the instruments, we have single beam instruments. Those are our simplest, and single beams are going to consist of filter-based instruments and single beam spectrophotometers. If it has the term spectro in it, just to recognize that, that means it's capable of scanning. Or it can acquire a spectra. Sometimes we may not ever want the ability to acquire a spectra, but sometimes we do. A dual beam instrument is going to be an instrument that automatically corrects for the blank, and then a multi-channel instrument. And we've used all of these. If you use the Spectronic 20, that's a single beam instrument. A dual beam's like the Shimadzu instrument that we used in the first couple of labs. And the multi-channel is the photodiode array that we use in our indicator lab. So a single beam instrument means simply that there's one beam of electromagnetic radiation, and that's passing through the one cell that's present. Now, it may be that we have another sample cell that we could move back and forth, and we could put both a blank and a sample in the instrument at once, but the light's only passing through one at a time. So there's going to be some type of a source, whether that's going to be a deuterium lamp or it's going to be a tungsten filament or both. That's going to give off what we call white light, all wavelengths, and then we need some wavelength selector. So it's either a filter or monochromator. A shutter is to set 0% T to measure dark current. Light goes through the sample. With the reference, we measure P naught. When it's going through the sample, we're measuring P. And then we've got some type of a detector to sense that. Now, the lowest end, or the cheapest instrument, and the simplest to use, are filter photometers. So they have an advantage is that they have an increased amount of light that goes through the sample using a filter. Percent T transmittance and filters, something like an interference filter, can be 70-80%. Okay, with a reasonable cost interference filter. You don't get that type of transmission through a monochromator. A good monochromator is going to give you 20% tops. Okay, most of the lights you lose out. They're inexpensive. The downside is that they require a filter to change the wavelength, and most of them are dedicated for a single analysis. And they're fairly low resolution. They don't have ability to resolve one signal from the other. All of the new ones today are going to have photodiodes in them. So that's the technology that they're going to use. So, let's see if I've got, here, I've got one back here. Here's an example of a handheld. So it looks like the size of a calculator, and it's basically got an on-off switch. It uses a round sample valve. This one's actually designed to analyze for copper, and it says copper on the top of it. This is created by a company called Patch. There's the market leaders in this technology, but these are designed as field kits. So you go into the environment or wherever you want to analyze a sample for copper content. You have reagents that are, there's going to be something here that's going to bind with copper. It's going to call its color. You fill the sample vial up to the mark. You dump the reagent in. You shake it. Wait 5 minutes. Stick it in the instrument. That's your read, and it's going to tell you the concentration.
And what is the concentration in?
Second,
What does it present the concentration in, like the units?
it's parts per million. So this one's in, it actually says milligrams per liter, which is a ppm. So if you wanted to analyze for like lead or arsenic or something in the environment, you could pack up a couple kits and complete. They sell a similar instrument that we have that Dr. Chiboni purchased that wasn't used much, but it uses the same technology in terms of their chemistry. They're got some really good chemistry, but they usually won't sell you these kits unless you purchase an instrument from them. And these things there's a couple of major problems with them. Number one, they cost typically like, these things are $1 a piece. And the other thing is they probably last a lot longer, but they sell them with like a shelf life of 2 years at the most. So you constantly have to replenish the kits. So yeah, they'll sell you this for $600, $700, but you're going to spend all your money in that. Dr. Chiboni has one next door. I'll show you this one.
They use them for like water samples?
All the time.
What are these right here?
Those are reference samples. So you can do a blank or a sample of mean concentration. So occasionally you have to calibrate it. So Dr. Chiboni, it's fascinating. They're things that it's nothing more than a spectrum. Do nothing but vibrate, but it's got the same type of just dead. It's got very specific reagents that you can put in it to get close to certain samples. So instead of you have to go to the labeling, look at things, or concepts go pop. But this was about $8,000 sale. So my knowledge, they're great.
We don't have any
Those samples, so we need to take it back over and do that. But this shows you the example of how portable something can be, and to the it really doesn't take a highly trained user, which is the advantage of this. It's hard to screw up as long as you follow the simple instructions.
So what type of people are using things like that? Like EPA work or like environmental?
EPA environmental is the environmental work is the mainstay. I mean, me personally, I would never do an analysis like that because I've got something that's a much, much higher quality instrument. And I can look up the chemistry to make something form the color or figure it out. But if you want something where you have to have a minimally trained expert to go get good results, that's where you use something like this. And they're widely used in the field. And Hatch is by far the leader in that technology. They've got a few patents on things, but for the most part, it's just they're so wide accepted, nobody else has been able to break into it. Single beam instruments, there are a couple of other manufacturers that still produce single beam instruments. You can get them with a tungsten lamp. A few of them have D2 lamps. There's just not many applications of single beams that's going to have D2s. Usually if you're going to go up to get a deuterium lamp, you're going to invest in a dual beam. Better quality ones may use a photomultiplier tube. Cheaper instruments are going to use a photodiode. Today they're going to use a grating for dispersion, and typically these are going to be hooked up to a computer for control. Now, remember the difference in the output of our lamps. On the left, I've got a deuterium lamp. It's and this is a log scale. It's good from the 200 to about 350. So by the time you go from the max here, a little past 200 to 350, you've dropped more than a power of 10 in your signal intensity. So beyond that, you have to switch over to a tungsten lamp, and a tungsten lamp gives through the visible. It's pretty weak down around this region. It'd be better if those two things overlapped a little bit, but they are what they are. Cost of a single beam instrument, anywhere from a couple of thousand up to maybe 8,000 effective bandwidths. They're going to vary again on the instrument, but typically a few nanometers. An accuracy of typically around a nanometer of wavelength accuracy. And typically they have something that's a feedback loop, so it senses the intensity coming from the source. And if the source is flickering, it senses that, or if the light bulbs will sometimes get a little brighter or a little dimmer. And it will sense that and adjust the feedback to the detector so that it gives you a constant output. And that's what gives you great precision. Typically 5,000ths of an absorbance unit is pretty reasonable. Now dual beams, now you take the monochromatic beam and you split it into two equal beams. Or you redirect that single beam. Two different options. One goes through the sample, the other one goes through the blank. And most of the scanning instruments are dual beams. Why do you think it would be an advantage to have a dual beam scanning instrument?
I mean, you can always have the reference, like blank.
Okay, and the fact that you've got both signals at once, it'll automatically subtract them out. So when you do a scan, you don't have to go back to subtract anything. It's automatically corrected. So this allows for automatic correction of your blank. Again, they're going to use the gratings, photomultiplier tubes for sensitivity. Low end cost is maybe going to be 8,000, and you can spend as much as you want to. The replacement for I had a couple of people quote a replacement for the old Shimatsu instrument that's we can't get a software upgrade for now, and if to get one with the specs that it has on it, it's going to be at least 35,000. Just to get one with the spectral capabilities that it has are around $20,000. Yes, that's expensive. And your effective bandwidths are less than 4 nanometers. But here's what you can get what you pay for. If you want one that's less than 1/100th of a nanometer, I can get it. All right, but the downside to it is that you're looking at money for something like that. So again, the big advantage is that the blank is automatically subtracted, so allows us to scan. All right, let's follow the light paths around and see how they look. Here are the two alternative designs. The one at the top uses a beam splitter, and the light comes through. There's going to be a shutter up here somewhere so you can get dark current. The light is split into two different beams. One of the portion of the beam goes to the reference cell, so this is where the blank's going to be. It measures P naught with the detector. The second beam goes through the sample and is reduced to P, and you've got a second detector in the system, and a difference amplifier looks at the two different detectors and takes the difference in the signals. Now, the downside to that is that if the detectors are not given an equal response, you can get a misleading signal. So this is kind of an older technology that we started using to start with. Today, most of the dual beam instruments use what's down at the bottom. You'll have your sources, and I say sources because if you're doing UV and vis, you have to have both lamps in there. Your wavelength selector is going to be a monochromator. There it goes onto a chopper, much like a flame spectrophotometer would be. So it's going to have a spinning mirror that's either transparent or it's going to be reflecting the light. If it's reflected, it goes up into the reference cell. Can then go through, it's got a one-way mirror here. Light can go through and hit the detector, or if it's not being reflected, it passes through the sample for P, and then it's reflected, hits the one-way mirror, hits the same detector, and then you amplify that signal based on a square wave. So the signal from that one would constantly be changing just like that in a flame instrument, and you would take the difference in the signal would be due to your sample. Okay. So now in reality, they're a little bit more complex. So this is the example of a variation of an instrument, and this is called a double dispersion instrument. This is what the Shimadzu is. What it does is it passes the radiation over the grating twice to try to minimize the amount of stray light. And these are what we're going to find in our highest resolution instruments. So something that can go in the hundredth of a nanometer range. Okay, so I'm going to make my highlighters small as I can. So you've got a source with either a tungsten lamp or deuterium, and it's going to switch back and forth. And that grinding sound that we hear with the Shimadzu instrument is actually the source. It's switching the mirror for the source. When it stops, when it scans, the light goes through and strikes a series of filter wheels, and that way it's going to have a cut off and cut on filters to isolate a certain region so you don't have order effects from the monochrometer. It goes through the first entrance slit, focuses on the grating, goes through the grating, comes out the first entrance slit, is redirected around and goes into a second entrance slit, restrikes the grating again, goes around, comes out that exit slit, then it's going to go into a beam splitter where the beam is either directed around through the sample, strikes the detector, or the beam is directed through the reference and then strikes the detector. That's a pretty complex set of steps. So this thing is all going to be sitting on what we call an optical bench that is typically going to be like everything's got to maintain its exact position. So an optical bench is typically a big heavy piece of steel that's something that's got a very low temperature coefficient, so it doesn't expand or contract with changes in temperature. And usually this is beefy, so you're talking about at least a piece of 3/4 inch steel to 1 inch steel on the base. So something like the Shimadzu, to move it, even though it looks like a small package and where the photodiode array weighs 15 pounds at the most, the Shimadzu weighs about 150 because of that chunk of steel, that optical bench that it's all mounted to. All right, moving to multi-channel instruments. So with multi-channel instruments, or what we call array-based detectors, they use a different type of technology. What they use is a diode array, and that diode array is going to be placed at the focal plane, and they allow the simultaneous detection of all data points. But the resolution is going to be limited by how many diodes are in that focal plane. So typically these things are going to cost somewhere from $6,000 to maybe $10,000 or $12,000. The replacement one that we bought in there, the instrument itself was about $10,000, but the software package that came with it was $16,000 for the package with the computer and the software, and it will do nothing without the software. So there's those external buttons, you can't get any readout of it. Now on the converse side of it, this is the photodiode array that's inside of this, and these you can get for, this is a technology that's changing every year. When we bought this first one, it was like $3,000, but this is like 12 years old. This is an old school one. Today you can get them for $600 or $700, and they're really a powerful alternative that we can use. The software packages they're designed for teaching tools. The downside of that one is it doesn't give you the ability to do zero. And I guess that's some agreement they have with other companies, because you can't blank a sample out, which to me is absolutely crazy. That's not an option. And it could be that this is such an old instrument, when they first realized they could do that technology with it, they didn't even get that excited about it. I'm sure the newer stuff can do it. That one, you can't do a zero. So you can't get a true absorbance number without making a measurement and manually subtracting it. The good thing about diode arrays is you can get very rapid scans. So if you have a sample that's changing continuously, you can monitor a spectra as a function of time. So if we look at examples, here's the example of a light path. You've got both a deuterium and a tungsten lamp. You've got a shutter that's going to go back and forth. So if you remember that instrument made a clicking sound when you zeroed, part of what happened is a shutter went in front of those sources and blocked all the light from hitting the detector. And the thing that makes this one different is that all wavelengths go through the sample. It's not just one wavelength goes through the sample. All the wavelengths of light go through the sample simultaneously. And then they're going to go through a pinhole slit and go through and strike the grating. And then what happens is that different wavelengths are reflected to different points on the focal plane, and the detector knows that this diode represents that wavelength. Your downside is you're going to be limited to the number of diodes that you have in that array. So common diodes that we had just a few years ago, a 1024 was a pretty big array, and typically this is the size of actually one of these things you're talking about. Well, this picture's blown up. You're talking about a picture that's 2 to 3 centimeters in the sensor where the focal plane is going to be. And it's a series of NP-type diodes where every one of these wells represents a different point where you can detect light at. Today, over this couple of centimeters, so this is, you're talking about something here that's typically in the neighborhood of 2 centimeters in length. You can put on the low end 1024. A few years ago, 4,000 diodes was as most as you could get, but I saw today they have a 12,000 diode one. So the more diodes you have in there, the more points you can do measurements, the higher your resolution becomes. So the downside to it is that if I go from a 1,000 to a 12,000, my data file just got 12 times bigger. So if you're collecting spectra continuously, that becomes an issue. The great thing about these detectors is they allow very high-speed detection. So in an example, when we combine chromatography, where we separate components out as a function of time, right, we can get a separation of a signal at a given wavelength versus time. But also, if I have a photodiode array detector that's continuously doing a scan, at every point in time, it's collecting a spectra. So if I think about it in this time slice, there is a spectra that is a spectra for that component, right? And it's continuously collecting these spectras, and it depends on how fast your signal's changing. The type of chromatography that I do, capillary electrophoresis, the peak widths are very narrow. So a peak here may only be in the neighborhood of 1 to 3 seconds wide in capillary electrophoresis. So that means to define that peak, I'd like to have at least 20 points in that. So that means I need to scan, I typically like to scan at 50 hertz, 50 times a second to acquire a spectra. So now I'm acquiring basically a 3D signal every 50th of a second. Each one of those data files is a 1/10 of a megabyte. So I can, even though it's a cool technology, I can fill up a hard drive easily in a month of data. So you have to figure out what data do you really need. You can get a lot more information with array-based detectors that's useful, because all this other time, it's worthless. So what you can do is you can say, okay, only tell it to turn on when it detects a peak. And there's no peaks, don't collect anything. That's a common way that we do it. But there's a threshold you have to set on what's a peak and what's not. So it knows what's a noise bump from what's a peak, and sometimes if you turn that on, you're going to miss something that's valuable. But this gives you more information about a signal. Not only am I stuck at looking at a signal at one wavelength, so if it were originally correct collected at, let's say, 280 nanometers. If I wanted to go back and compare what the signal looked like at 254, I could see that or regenerate that if I needed to. A lot of value with array-based detectors. Increased cost, increased data collection, so there's an issue with it. All right, so here's an example of the hatch ones that we looked at, the handhelds. Typically, you call this a photometer because you're not doing any scanning. The wavelength selection is controlled by typically some type of a filter that's in here. This says that there's a prism, and that's not the technology they use. They have an LED light source, and then typically going to have a wavelength selector sitting right in front of a photodiode detector. The light typically passes through the sample twice to increase the effective path length in the system. This is one very similar. This is one for chlorine, but this is just like the ones in the blue box. This is a higher end one. This one may have a wavelength selector in it because it would be capable of doing 4 types of analyses. But they're really simple technology, and they're all designed to be completely containable. You can take the instruments, and there's a beauty today of fiber optics that you can transmit light for very, very long distances with very little loss of signal intensity. So you can do any analysis that we can think about doing. You could couple it to fiber optics and now take that remote. So you could take it remote in the sense that you could hook it up to your instrument. Instead of having a cuvette, you could stick a fiber optic probe into your sample, and you could have the light come in, go down, hit a mirror, bounce back out, and go back out. You control this gap 2 times that is your path length. And you could adjust that for your concentration on your sample. But there's no cuvettes to clean. So you just go from sample to sample. Today with fiber optic probes, this is a common design. They use these, what we call light pipes, the fiber optics. And we can throw these inside of something where we need very, very small volumes. Here, a microcentrifuge tube. You can measure spectra with microliter volumes pretty easily with these guys. I was at a plant at the company I worked for at Monsanto, and we had a plant where we monitored the olefins that were coming out of reactors by putting fiber optic probes actually in the streams of liquid going through, and then we ran the probes back to the control plant so they could monitor what was going on constantly. And the spectrophotometer was sitting in the control room. They didn't want to put it out in the harsh environments of the plant, but it was just fiber optic cables that were transmitting that signal back in. One of the other technologies is to even go to smaller volumes, is to go to nanoliter volumes. And there's a terminology called the nano drop. Dr. Paida has one of these. I've never seen it used, but I'm glad y'all got to use it. So I'm glad it's functional. I've just never been down there and seen the thing in use. But it's basically a miniature diode array spectrometer, and it creates the sample cell you put a small amount of liquid on here, and you drop the top down. It creates surface tension between the two, and that becomes your optical cell. So you can get full spectra, and you can't get away with nanoliter volumes, but they're getting pretty low. So a few hundred nanoliters today work, but they're a cuvette-less design. And this is when you've got limited sample. This is the way to go. Okay, this is the things like DNA expression. You're looking at results of PCR. What did y'all do it for?
Pretty sure we did that PCR.
Okay, so that's
it, and then we put it in the.
That's a common thing where you've got a very limited volume of sample available. That's what you use this technology for, and this is probably very similar to the one that y'all used. Okay, so and then we go back to the old school extremes. So found in every teaching facility, and typically going to be found in almost every lab because of the simplicity of the instrument. This is what we call the Spectronic 20. And the 20D means that it has a digital output. And the plus means that it has a photodiode as the detector, which gives it long-term stability. A couple of simple places or measurements on these where the sample goes in, your wavelength selector, and then you have two different knobs. This is your on off and where you set 0 versus 100% T. So the line in these is pretty simple. Back down here in the bottom in the back, there's a tungsten lamp. Light goes through, is collimated, strikes a grating. That grating is spring loaded on a swivel, and that's hooked up to a gear mechanism, which is hooked to this. When you turn this guy, you're turning this cam back and forth, which makes your focal plane move back and forth in this direction. And you change the wavelength at a time to go through a very small exit slit. The 20 represents a 20 nanometer bandwidth. That's where that comes from, the name. Goes through the sample and strikes a photodiode detector. Now, the newer ones all have the switch on them that lets you get rid of orders. So you just have to be careful. Are you below the, whatever the magic number is, 600 nanometers or above 600 nanometers? Because if you're above 600 nanometers, it allows all the light to pass. If it's below 600, it has a band pass that cuts off high order radiation. Otherwise, if you had it set on, let's say 620, it would also be transmitting second order radiation through that at whatever that divided by 2 is. So, all right, so simple technology. Here's kind of a better image of what the Shimadzu looks like. This is actually a Perkin-Elmer instrument, which is now the Cary Eclipse line, but the optical path and how things are hooked onto the optical bench with it. So it uses choppers to redirect the signal. Whenever you have here's the monochromator box, so hopefully you recognize the Sursney Turner design. Whenever you see that W in the light path, that's a Sursney Turner. You can't make that guy too small, okay? Because the amount of separation of the light that you're going to ultimately get going from the focusing mirror to this length on the focal plane where the exit slit is, that's got to be, you maximize that to get the best separation. So if you get close, you're not going to get good separation. So these are always going to be larger boxes if you want to think about it. You can't miniaturize that design. The diodes, however, can be miniaturized. You can make them much, much smaller. But typically, the higher the resolution, the bigger the footprint the instrument's going to be. And that's just the trade-off that you have to have. On this style of instrument, the slit widths are adjustable, so there are servo motors that control exactly how wide these slits are, and those are things that, with high precision, go back and forth and adjust that. Typically, they're going to work in pairs. But the light's bounced all around through those things, and every one of these mirrors has to be very, very securely attached so that there's no movement. I mean, if a mirror were to shift because the instrument's bumped, everything out of alignment. If you ever take the top off of one, it's just a big black board, and it's black so it doesn't reflect light on the inside. Everything will be painted black so you don't get stray light in any way. And there's tons of screws. Every mirror has multiple screws there. So when it's there, and typically they put something like a thread freezer. I'm blanking on my name. You put on bolts to keep them from back.
Red tape or.
Yeah, it just locks it basically, and then if you have to break it loose and move it, it's really hard to do, but it keeps a bolt from backing out over time. And then going to the other extreme, this is even an older version than the one we have. This one is the 2000 series, so it has half the resolution in terms of the number of diodes there, but this is a D2 source. So you can actually get this little miniature D2 source for about $1,200, and you can do a UV vis spectra out of it. Where ours, this one, I'll just plug it in to show you what it uses. It So it came on for a second and then it went away. But it has a little photodiode in here. The light kind of looks purplish. It's not pure white light coming out of it, but it, for sometimes that's what you need to do the job. Okay, that's as short as 13 is. 14 is going to be about the same length. So it's we'll spend 2 days most on chapter 14, and then we'll continue to just roll through this material. After this, we'll do fluorescence. Behind fluorescence,